In this video, we'll cover the problem number of connected components in an undirected graph. So if you look at this graph, you'll see that we have 0, 1, and 2 as three nodes that are kind of connected to each other in some group. So we'll define this as one connected component right here. Then we have another connected component that contains the 3 and 4 node. So you'll see that if nodes are connected directly or indirectly, we consider them to be part of the same connected component. So 2 and 0 are part of the same connected component because they're connected indirectly through the one node. And in this question, we simply want to count the number of connected components in the given graph. So for this example, you'll see that there are two connected components, this one on the left and then this one on the right. For this example, you'll see that these nodes are actually all indirectly connected with each other, so there is exactly one connected component here. In terms of our inputs from the question, you'll see we're given an integer n, which tells us how many nodes are in the graph. And then we have an array of edges, which is formatted like this. If we have a subarray 0, 1, it means that there is an edge between the 0 and 1 nodes. And it's an undirected graph, so we can go either direction. We can go from 0 to 1 or from 1 to 0. Now, we basically want to count each connected component. So we need some entry point into each connected component. In this example, example number 1, we'd probably use 0 as our entry point into the left connected component and 3 as our entry point into the right connected component. However, the numbers 0 and 3 are somewhat arbitrary. There's no way for us to actually know that we should be starting at 0 and 3. So what we're going to do is we're just going to iterate over every single node in our graph. And at every node, we are going to try to explore its whole component. So for every node, what we're going to say is, all right, I'm going to increment my counter and say, hey, I just found a new connected component. So when we hit 0, we'll say, I found a new connected component by incrementing our counter. However, we want to make sure that 1 and 2 do not increment our counter because they are the same connected component. So what we're going to do is at the 0 node, after we increment our counter, we're going to explore the entire component that is connected to the 0 node and mark all of them as visited. And then we'll just say if a node has already been visited, don't increment our counter and just skip ahead. So then the core logic for this question just becomes, how do I traverse through one connected component if I'm given an entry point like the 0 node? And we can use either breadth first or depth first search for this. In this example, I'm going to use breadth first search, but it's completely fine to use a depth first traversal here as well. So that's the gist of the algorithm. Just quickly to summarize, we'll iterate over every node. If the node is unvisited, we're going to increment our counter and then mark its entire component as visited using a breadth first traversal. Cool. All right, let's go ahead and get started with coding this. So to get started, I'm going to convert this function to use ES6 arrow function syntax. I'm also going to rename this parameter to be named numNode so it's a little bit clearer. Now, the first thing we want to do is we want to convert this input edges into a graph that's a little bit more usable for us. So we're going to map every node to an array of its neighbors. And so we'll have a separate function build graph that does that. We'll write that in a little bit. Other than that, we obviously will need a num connected components variable to track how many connected components we have. And we're going to need a visited set as well so we can track which nodes we've already visited so that we don't visit the same node multiple times. Other than that, we're going to iterate over every node, so we'll start at 0, because that's what the first node is here. We'll continue so long as node is not less than numNodes, and we'll just increment our node at each iteration. At this point, we'll say if the node has been visited, we don't want to do anything, we just want to skip it, because we've kind of accounted for this component in a previous iteration. Otherwise, if we have an unvisited node, we know that we have a new connected component. So we're going to increment our counter. Then we also want to mark the entire component as visited. So I'll have a function that does that. and it needs to know what node we're on. It needs to have the graph so we can kind of find neighbors and traverse the graph. And then it also needs the visited set so it can mark things as visited. In the end, I'm simply going to return the number of connected components. And so this is the kind of outline for our algorithm. Now we need to implement the build graph function and the mark component as visited function. We'll start with the build graph function. This one is pretty standard. You probably have seen this before. But we're going to create a graph here, which will be a JavaScript object, and we'll return it in the end. In between, we'll iterate over every single one of our edges. And let's destructure out the two nodes. So we have a first node and a second node. Notice that I'm not naming them something like from and to or source and destination because these are undirected edges. So there is no real source or destination. We can go either direction. Once we have both of these nodes, we can simply say, we'll look at the array that is graph at node 1 and push node 2 to say we can get from node 1 to node 2, and then we'll do the other direction. So we'll say we can get from node 2 to node 1. Now there's one edge case we want to handle, which is what if node 1 is not in graph yet? Then we're going to have undefined right here, and we're going to try to push into it. So we're just going to say if node 1 is not in the graph, create an empty object. So I'm going to create a boolean for this, and you'll see why in a second. But we'll say node 1 in graph is going to be graph.hasOwnProperty node 1. It's important here that we're using hasOwnProperty instead of doing something like graph or node 1 in graph, or something like graph at node 1 is not equal to undefined. Node 1 in graph will actually look at elements that are on the prototype of an object itself. So it's not only looking for keys that you have set, it also looks for some other special keys which can cause problems. And for the undefined case, it's also, there are times where someone will explicitly set something to be undefined. Really what we want to check is whether or not node 1 exists as a key on the graph, as a user set key on the graph. And the way you do that in JavaScript is with the hasOwnProperty method. So it's important that you make sure to use that. And in a real interview, you'd want to explain why you're using that so that you can show the interviewer that you have a solid understanding of JavaScript and the nuances of how objects are implemented. But with that out of the way, we simply want to say if node 1 is not in our graph, add it to our graph and just create an empty array so that down here we can push to it. And we're doing the same thing for node 2 as well. All right, now lastly, we want to implement our mark component as visited function. This is going to take in a start node, it's going to take in our graph, and a visited set. And this is going to be our breadth first traversal. So we'll create our queue. So we'll have a new queue, and we're going to add our start node to the queue. Remember, our goal here is kind of start at something like the 0 node, go through the entire component, and mark every single node in that component as visited. So we'll have our standard BFS condition here, so long as the queue size is greater than 0. We have our 3 steps. We have remove node, process node, and add neighbors. Removing a node is easy. We'll just say node equals queue.dequeue. We'll skip the process node for a second, and we will grab our neighbors. So we'll say neighbors is graph at node. And note, it's actually possible that node is not in graph. So we'll add something here. We'll do our node in graph check. We'll say graph.hasOwnProperty node. And if the node is not in the graph, we can simply continue. We don't need to explore any neighbors. Otherwise, if we do have neighbors, we'll iterate over each neighbor of our neighbors. And we want to simply add them to the queue. So we'll say queue.queue to add the neighbor, except we want to skip neighbors that have already been visited. So we'll just say if visited.has the neighbor, just continue, no need to add it to the queue. This is pretty standard BFS stuff thus far. Now we have the process node step, which is still remaining. And the process node step answers the question of what do we want to do for each node? And what we want to do for each node in this component is mark it as visited. So simply we can just do visited.add our node. And with this, our mark component as visited function should be able to execute a breadth-first traversal over some component from the start node and mark the entire component as visited. So we can go ahead and see if our code works. Okay, it works on this case, and if we submit it, let's see if it works overall. Great.